Okay, so we started factorization of polynomials, univariate polynomials over a field, right? Because that polynomial ring is a unique factorization domain. We saw some simple examples manifesting that roots are very closely related to field. So as you change the field, the roots and the factorization pattern changes. In fact, there may not be any factors if you change the field. Over complex, it's the other extreme. Every polynomial actually factors non-trivially all the way up to degree 1. So such fields are called algebraically closed. But now we will actually come down to something very different, a place where there is no geometry, which is finite field. So this is the example which computer science cares the most about. Almost all the practical applications are actually based on finite fields. So be it combinatorial constructions or error correcting codes and so on. So we'll see some examples of those applications once we are done with some basic polynomial factorization. So yeah, later we will see factorization over Q. So this order we will follow because believe it or not, factorization over Q or over integers will actually need factorization over finite fields. Okay, so once you know these methods, then we will use these roots or these factors to actually get integral factors. So that has to be done in this order. So finite fields, you must have seen enough properties and proved some of them in this first assignment. Finite fields are, so these are discrete objects. Useful in combinatorics and computer science. And the construction of this, as you have seen, is basically based on a prime, right? So you start with a prime characteristic P. So you are also allowed to take P equal to 2. So that will be a field with only 2 elements, right? 0, 1, and you can add them and you can multiply them, and arithmetic is mod 2. So in general, you have shown that Z modulo P, which we will denote, actually let's not use this, we'll denote it by quotienting. So Z mod P ideal is a, well, first of all it's a ring arithmetic and then it's actually a field. So how do you show that every element is invertible in this except 0, of course? Right, so this is based on just GCD. So for any element, non-zero element A, you take the GCD of A and P, it will be 1. So you have UA plus VP equal to 1, which means that U is inverse of A. So that is a simple proof. More interesting things happen when you want field of size P square. So this is a field of size P. What is a field of size P square? That you have constructed in the first assignment. So that is done by picking irreducible polynomials. So in this case of degree 2. Be an irreducible polynomial of degree, let's say n, with fp coefficients. So it's in the polynomial ring fpx. So this will be key to pick a irreducible polynomial. Then now when you do arithmetic mod this polynomial, that it will be a field, and it will be a bigger field. So fpx mod f, this is a field because every element here is invertible, again by Bezout identity, because f is irreducible, so it behaves the same as you saw in the proof of the above statement. F is kind of a prime, so any polynomial a will again be the GCD with f will be 1, or a itself is 0 in this ring, in this arithmetic. So for a non-zero a comma f, GCD is 1, so you get ua plus vf equal to 1. So every element has an inverse. So this is a field, and this field is called, we'll write it as fp to the n. It's also written as in the literature Galois field. So gf of size p raised to n. Okay, but usually we write f of f sub p raised to n. So either of these definitions.
But if R is a ring, then will Rx modulo f for an irreducible f also be a field or a ring?
No, if you talk about general rings, then behavior will depend on R. I mean, if you start with an R which has 0 divisors, then the 0 divisors will remain no matter what you do. So it cannot be a field. So you have to start with a field to have any hope of getting a field extension. So this, in fact, in the assignment you must have shown that this is unique up to field isomorphism, right? So this is actually the field. So this is the field of size p raised to n. So there is only one field of this size. So okay, so for every prime power there is a unique field, and vice versa. So every finite field is of size prime power. Okay, so this is a nice characterization that you have shown. And so we will usually denote prime powers by q. And so yeah, in this property I also want to embed something about the bit size. So how many bits will a single element require when you want to represent it practically? N log p. Yeah, so or if in terms of q it is log q. So the representation requires log q many bits. So that needs to be remembered. Okay, so finite fields of size q, one element will not mean one bit, it will actually mean log q many bits. Also, what is the structure of fp to the n over fp? It is a vector space. It's a field extension, hence it's also a vector space. And how many basis elements are there? N basis elements are there, right? So that is another way to represent an element in this field. You can be given n numbers. right? So these n numbers, each number should be thought of as an element in FP. So it's a number between 0, sorry?
Of size, bit size log.
Yeah, so hence this number will have magnitude 0 to p minus 1 and bit size log p. And there are n of those, so it's n log p, which is also the same as log q. Right, so these are all, so this actually is the standard representation. You think of an element as n numbers. And when n is 1, it's only one number, which is clear because it's an integer between 0 to p minus 1. When n is equal to 2, then you are talking about two numbers. Right, so that is how we will, whenever we say a field is given or we are working over a field, that is the representation. Okay, without exception, this is the underlying representation we'll talk about, and we'll assume, and then the time complexity will be in terms of this representation. Okay, so it's completely explicit discussion. This is not abstract. Okay, so for example, if you look at x square plus x plus 1 interpreted in f2x, then is this polynomial reducible or irreducible? How do you prove it?
It would have a root, but both 0 and 1.
Exactly. So there are only two roots possible, and both of them will give you 1. So this is an irreducible polynomial. So that gives you a simple quadratic extension over f2. So GF4 is, you can think of it as just f2x mod this. So this is the field GF4, and it has very few elements, right? So it has 1, well, it has 0 and 1 from f2. And what else? It has x and it has 1 plus x, right? So these are the only elements in this field. Any polynomial in x will map to one of these 4, right? So x square maps to what? X square in this ring is equal to what? It is equal to x plus 1, right? And x square plus 1 is then equal to x, and so on. So similarly, you can think of x cube. All the other higher degree monomials reduce to this. So hence, when you multiply elements, so when you multiply x with 1 plus x, multiplication actually requires one polynomial multiplication operation and then also division, right? So all those things are again implicit whenever we'll talk about complexity, that you have to actually do division here. There was a question in the assignment where you must have done that as well. So those things now we'll just assume when we talk about complexity, because you have seen polynomial multiplication, you have seen integer division, and similarly you can also do polynomial division. So everything you can do in O tilde linear time. Yes, so these are the kind of fields you are given in the input, and over this there is a polynomial given which you want to factor, right? That is our that is the setting. That would be your input instance. So maybe I give that example also. So you are given maybe a polynomial fx, which is say x square plus little x. So this is a polynomial GF4 with this formal variable x. So you may be given this big F in the input. So GF4 is in the input, and then big X square plus small x is a polynomial over the finite field, right? And then somebody asks you to factorize this, which means find the root of this, which is also the same as talking about finding a square root of x, little x, right? So whether it exists in the finite field or not will be a related question. Or prove that this is irreducible, right? So the question of irreducibility testing, root finding, factorizing for big F is our goal now. How will you do this efficiently? Any questions? So we'll now move towards such algorithms. Okay, how is that done? So first of all, how is irreducibility testing done? Given this polynomial big F, how do you quickly decide on a computer that it's irreducible? This is a very simple example. This you can actually see that it's irreducible because square root of small x is non-existent. Is it?
1x.
Yeah, it is actually there. So this will factorize as what? Yeah, so let us write down. It actually factorizes. So this is actually big X square plus, what is the factorization? Say that again.
X plus x whole square.
Big
Big
X,
X plus small x whole square.
I somehow think this is false.
Small x plus 1. It's big X plus small x plus 1 whole square.
Okay, yeah, that is correct. So this is how it factorizes. Yeah, so it's actually a good example. It seems to be irreducible, but then you can see that small x plus 1 is a repeated root of this, right? So now imagine this problem if your big F was arbitrary degree d, right? So in that case, actually, this will be a real problem, just to check whether it is irreducible. Forget about finding root or finding factors, right? So that will be our first goal. Maybe we'll finish it today. How do you check irreducibility? Okay, so towards that, let us now repeat some of the properties that you have seen in the homework. Okay, all those things will be now used. So you have seen that this field FQ minus 0, so FQ star, we call it FQ star. This is a, yeah, it is because it's a field, this has to be multiplicative group, but there is more structure to this. It's a cyclic group. So this you know is a cyclic group of size q minus 1. And this means in particular, actually you just needed abelian group of size q minus 1 also. So what I want to deduce is that any element you take from this e raised to q minus 1 is 1, right? Because just because it's an abelian group of size q minus 1, any element if you multiply that many times will give you in the end 1, because the multiplicative order of any element, first of all it is finite, and second you can show it will divide q minus 1. So if you raise a to q minus 1, you will always get 1. That is just by the structure of abelian groups. And if you also include 0, then you have to look at a raised to q, which is a, right? So this is satisfied by all a in the finite field. So this is a fundamental identity Uh, its special cases have names, so this is also called FLT, Fermat's Little theorem. So when Q is a prime, then any number, if you multiply it Q many times, you get the remainder same as A, mod P, or in this case mod Q. But when Q is when Q is P square, then this is different, right? This is not really, A is not really a number, it's an element in a bigger field. But this continues to hold. So its special case is called Fermat's Little theorem. So Fermat's Little theorem has multiple proofs. This is one of them. This is the field-based proof. Any questions?
So we are assuming Q to be prime.
Q? No. Q is so FQ is a finite field. Whenever we will say Q, there will be no assumption except that it's a prime power. Yeah, so for finite field, you can continue calling this FLT. This is also called Frobenius action actually. That's another name for this. So if you raise any element by the field size, that is one of the Frobenius actions. In this case, it is a trivial action because A raised to Q will give you the same thing back, which is A. But you could have instead raised A to P, right? So that is actually called the Frobenius automorphism. There are multiple names for this. Okay. So now based on that identity, we'll design an irreducibility test for an input polynomial. Discuss what property we are interested in. So suppose you are given a polynomial, we continue to call it big F. Okay, you are given this with coefficients in FQ. It's a univariate polynomial. So you want to test whether this polynomial is irreducible. So what we intend to do is we will suppose you want to check whether this has a root, FQ root, right? So I want to take GCD of this with something. So by looking at the previous equation, what should you take GCD of this with? So if big F has a root, then it will satisfy A to the Q minus A, right? So you should actually then take GCD with x to the Q minus x, right? So this F is okay, let me make this as before big X. So F is a polynomial in big X. And you compute the GCD of these two polynomials. So now if the GCD is 1, then it means that big F has no root, right? Because if it had a root A, then x minus A will divide this. And x minus A also divides the second polynomial. So x minus A will definitely divide the GCD. So this being 1 actually means that there is no big F has no root. Now, more interestingly, this test can be extended to cover quadratic factors. So, if big F has no root, it may still have a quadratic irreducible factor, right. So, for that the test you will do is x to the q square minus x, and then so on. Okay, this is the intended algorithm, that you keep taking GCD of big F with these Frobenius type polynomials, Frobenius inspired polynomials. So, if you take GCD with x to the q minus x, you are filtering out roots. If you take GCD with x to the q square minus x, then you are filtering out quadratic, well, both roots and quadratic irreducibles. So, this sequence of GCDs we want to compute. So, that is the intention. Now, the why should such a thing work is this theorem. So, big F factorizes say its degree is d if and only if there is some I there is some I such that the GCD of big F with x to the q to the I minus x and GCD with respect to the variable big X, both of them are univariates over the underlying finite field. So, you compute the GCD and this should not be 1. So, if big F has a non-trivial factor, then the GCD will not be 1, and if the GCD is not 1, then there will be a irreducible factor. In fact, just the GCD operation will give you a factor of big F. Okay, it's a constructive proof. So, we will prove this theorem. It has an elementary proof, but once you have the proof, how can you use this in an algorithm? How will you compute this GCD? In how much time?
I log q for every I.
Sorry?
I log q for every. Oh, m of I log q for every.
I log q, but the degree of this is q to the I.
That is the degree of.
So, well, take I equal to 1. So, this is, if you are taking GCD with x to the q minus x, that is a q degree polynomial, right. So, if you just use Euclid GCD directly, then this will give you q in the time complexity, but since your input size was log q or d plus log q or d times log q. So, let me write that down. The input size in this case is d times log q. So, you want your time complexity to be polynomial in d log q. If you spend time q, then it's already exponential, right. So, how do you compute this GCD faster than q time? Well, you should reduce x to the q mod f, compute the remainder. So, there was a question in the assignment that this exponentiation can be done in by log q repeated squaring. So, you compute big X square, then big X4, then big X8, 16 and so on. So, this will only take log q iterations. So, very quickly you can actually compute the remainder of x to the q mod f, and then you work with the remainder instead of x to the q, because it does not change the GCD. Right, GCD is invariant if you divide one argument with the other. So that is the thing. So this polynomial, this Frobenius polynomial happens to be so nice that this gives you an immediate algorithm. Okay. So that is a very lucky break. It may not have been this easy otherwise to compute.
We directly take I equal to d minus 1 in the first step.
Yeah.
It is sufficient.
No. Let us first look at the proof of this. Why is this thing true? Then you should answer this question.
Sir, if we get a quadratic irreducible of f, then in the extension q square we will be getting a root of that.
Yeah, that is the idea.
That is the idea.
Yeah. Yeah, so if big F is, suppose it is itself quadratic, irreducible, then its root is available in FQ square, in Galois field of size Q square. So hence the GCD will come out. I mean, big F will actually divide the whole thing in that case. It cannot be, GCD cannot be 1. So yeah, that is the basic idea. So we'll just build on that to finish this proof. So let's do the forward direction. So we assume big F is reducible. So let H dividing F be an irreducible factor of degree d prime. Between 1 and d minus 1. Okay, it's a non-trivial irreducible factor of F. So now you look at FQ x mod H. So what is this? This is the Galois field, right? Of size? Exactly. So this is also a finite field. It's bigger than FQ, possibly bigger than FQ, and has size q to the d prime. So what you can say now is, now you use the FLT or Frobenius action identity. So that will give you x to the q d prime is the same as x mod h. Right, h will divide x to the q d prime minus x, in other words. So h divides this polynomial, and h also divides original f. Sorry, I should use capital F there. I've changed the notation. So h divides your input polynomial by assumption, and h also divides this by Frobenius action. So h divides the GCD. Right, so hence GCD cannot come out to be 1 because h is not 1. H is degree at least 1. So that part is done. Any questions? Okay, let's prove the converse now. So converse is more interesting. So suppose for some I you get the GCD, well, we'll actually do it the contrapositive way. So you want to show that the conclusion implies the premise, right? So instead we'll show that if big F is irreducible, then the GCD is 1. Okay, let us prove the contrapositive. So say big F is irreducible. and I be the least number such that the GCD of these two polynomials is not 1. So, we actually intend to get a contradiction. Okay, we are assuming that big F is irreducible, and we are assuming that the GCD is not 1 for some I. So, if we get a contradiction, then we are done, right? So, let us see what the contradiction is. So, well, so if big F is irreducible and the GCD exists, what does that mean? It has to exactly divide. GCD has to be big F. That's the only option. Right? And so write this as Frobenius action. So x to the q to the I is actually x mod big F, which is irreducible. So from this, okay, let me. So from this, what can you say about elements in this quotient ring? Any element A that you take in this quotient ring FQX mod Fx. So first of all, this ring is what? Why is it a field? Yeah, because we have assumed big F to be irreducible, right? So this is a field. What can you say about the elements in this, which is again a finite field? Elements A in this finite field.
They're all roots of
Every A will satisfy the previous Frobenius action. Why is that? That is not trivial. How do you show this? How do you show that A raised to Q raised to I is also A? By using the previous congruence.
Ax is a polynomial, so a raised to q raised to power I will distribute.
Yeah, so you use the fact that Q raised to I distributes over sum.
binomial identity.
Yeah, use the binomial identity. So since y plus z raised to q is the same as y to the q plus z to the q. And this is actually true simply mod p. So your characteristic is p and q is a power of p. Okay, so no matter how many powers you put over y plus z, they will distribute. The exponentiation operator will distribute over sum. So the reason is that when you do binomial expansion, the other coefficients are q choose I, and q choose I is 0 mod p. It's divisible by p. Okay. So this is true by binomials. So that is a nice property to remember. This is again a consequence of Frobenius action. So this in particular shows that raising exponentiating by p preserves addition and multiplication. So it's actually it's first of all a homomorphism. You can see that it's also an automorphism. Okay, so that so maybe I should write that. That should also be remembered. So here meaning in the case of finite fields, whenever you exponentiate by p, you actually get a homomorphism which happens to be an automorphism, an endomorphism which is actually an automorphism. Okay, this is a very non-trivial fact and also a very useful one. So, yeah, so coming back to the last implication, what you have learned is that every field element in FQX mod F satisfies this Q to the I Frobenius action. It's a trivial action. So, which means what?
Most people are used at most people are elements because any polynomial can have at most degree many roots in a field.
Yeah, but you can make a even more precise statement. So you can actually say that q raised to d minus 1 will divide q raised to I minus 1. You can actually get an equality in terms of exponents. So that argument goes as follows. So let me give it a name. Let me call it F sub q prime. So this field except 0 is actually a cyclic group. Of size, field size minus 1, right? What is the field size? Q prime, which is q to the d. So this is a cyclic group of size q to the d minus 1. Every element here satisfies this q to the I trivial Frobenius action, so it means that generator as well. A generator has order q to the d minus 1. So which means that q raised to d minus 1 has to divide q raised to I minus 1. Right? Which means what? Yeah, in particular it means that d is less than equal to I, but that is not possible. Right? The I with which we started with was between 1 and d minus 1, so that's the contradiction. Okay, so this contradiction means that when you start with an irreducible input, then you get all GCDs 1. So this means that converse holds. Any questions? So this is a fundamental property, and its proof, as you can see, uses almost all the basic properties of finite fields. Right? This is why you were prepared by assignment 1. So building on that, you can actually show that an input polynomial is reducible if and only if for some I, this GCD is not 1. Or equivalently, an input polynomial is irreducible if all these GCDs happen to be 1.
I think we can also write I is less than root d plus 1.
I is less than root d.
We have greater than root d factor.
I don't want to say that. Yeah, d by 2 we can say, yes. So if the input polynomial factors, then clearly there will be a factor of d by 2 degree or less. So so that optimization you can do. You need to only go up to d by 2. So let me just say it here. So d by 2, it's a bad notation. I mean, yeah, let me use the range. So 1 less than equal to I less than equal to d by 2 works. Any questions? Okay. Yeah, so now the algorithm, all the constituents are there. These checks are already so they are in a good form that you can just implement them in a straightforward way using the basic arithmetic. So using the arithmetic of integers and using the arithmetic of polynomials. On top of that, you can implement everything and it will be really fast. So let us just for formality see the algorithm. And also we want to analyze the exact time complexity. So in the input you are given a degree d polynomial big F and a finite field FQ. The finite field has to be properly given in the natural representation. Otherwise, you cannot give the coefficients of big F. So finite field is given and then the polynomial is given. So this is just a for loop. But before that, there was a question you had, right, Pranav? What was the question?
Just for I equal to d minus.
Yeah, maybe we address that first because that's a good property. In the proof, so this proof actually tells you more. So in particular, if there is this factor h of if there is an irreducible factor h of degree d prime, what are the i's which will work? I mean the i's where you will see not 1. Yeah, that is not clear. Yeah, so actually the correct characterization is that I equal to d prime will give you a certificate, so GCD not 1. But then after d prime, the next step or next I will be 2d prime. Okay, so you will actually get in multiples of d prime. So that is a good characterization because if you look at the converse, it means that what are the factors of x to the q to the I minus x? What is the degree of the irreducible factors of x to the q to the I minus x? Yeah, so they are actually irreducible polynomials of degree dividing I. Okay, so it's not that x to the q to the I minus x will be divisible by all the irreducibles up to degree I. It's actually only factors of I. So did you understand that h here of degree d prime will divide for I equal to d prime and then I equal to 2d prime? Did you understand that property? So why wouldn't it divide for things in the middle between d prime and 2d prime? What is the reason? So that reason actually is in this slide. So you have to go through this. So in particular, if you look at the last condition, q raised to d minus 1 divides q raised to I minus 1, what can you deduce from that? Right? Yeah, so you actually deduce something stronger than what I have written. you actually deduce from here that D divides I. Okay. So this slide is proving another interesting property over finite fields, that this x to the q to the I minus x, all its irreducible factors have a degree that divides I, and they are all of them. Nothing is missed. Okay, so this x to the q to the I minus x actually contains all the irreducible polynomials whose degree divides I. This, I mean, as a sanity check, you can look at I equal to 1. So x to the q minus x contains actually all the irreducible polynomials of degree 1, which is just roots. And when you go to x to the q square minus x, you will get all the roots and all the quadratic irreducibles, and so on.
Cubic will won't get quadratic.
Exactly. So in the case of x to the q cube minus x, the quadratic factors will be missing. So there will be all linear factors possible and all cubic irreducibles possible. Okay, so actually this slide is quite important. The parts of the proof here tell you a lot more structure over finite fields. Okay. So this is just a for loop. So in case the GCD is not 1, then you have a certificate of reducibility. And this is written very abstractly. So in practice, you actually have to do this by repeated squaring. So this step is loaded. It is not just direct application of Euclid GCD, but first you have to do this assignment question. You have to do repeated squaring to compute what is x to the q to the I mod f. F is low degree, so this computation is actually low degree computation. So you can do this efficiently, and then you replace x to the q to the I by that remainder. Then you invoke Euclid GCD. Okay. So this can be done.
I think it's invoking even the other properties, GCD property, because GCD of AB is GCD of.
Yeah, that you can do. Yes. Okay. And what do you do in the next step? Well, not much. So if the program has not halted yet, so then it went from I equal to 1 to I equal to d by 2, and always the GCD was 1. So it means that big F is irreducible. Okay, so only when the whole for loop has gone through, you declare irreducibility. That's the certificate of irreducibility. Is this clear? So the proof of correctness of this algorithm should be clear by the theorem. Right? That is straightforward. It's only the time complexity that we have to. So what is that? The for loop is d many times. The GCD computation, before that you have to compute x to the q to the I mod f, right? How much is that? That is again I log q, so d log q many squarings. And for every squaring, so that is a single multiplication operation, right? Mod, yeah, so modulo this polynomial of degree d and also the finite field calculations. So actually we can separate the finite field calculations. We can just say O tilde d many finite field operations. And right, so now you have brought down x to the q to the I to a degree d minus 1 polynomial at most, and you will run Euclid GCD. So that will be how much? That will be linear time, soft to linear. So that will be O tilde d. So these many FQ operations. Okay. Any questions? So this is the time complexity, which well, ultimately we can talk about actually bit operations as well. So this is at most d cube log q which is at most FQ operations will take how much time? Just log O tilde log q. So this is the actual time. Okay. In the input you were given a binary string, and in the output you will give a bit answer, 0 or 1, irreducible or reducible. And in the middle, the number of bit operations which you can think of as a second is d cube times log square q overall, with hidden log factors also. So this is O tilde, so there is also some multiplication by log d and log q, but that we can assume is very small. Okay, so it's a cubic time irreducibility test. Any questions?
Should be FP, like FP operation, because when we are doing ZD, we are taking it as polynomial.
Yeah, we are not going all the way to FP, so let us just stop at FQ. FQ is the base field for us. We don't want to go all the way. We also don't need, because FQ, how we will implement in O tilde log q bit operations, in that detail it is hidden, that you convert FQ into n FP elements and then you do addition multiplication. All that we don't have to go into. So that is why we abstract these things out, simplifies the calculation. Otherwise, I mean, when you look at the full implementation, there is a lot of things that go on. It won't be just these many lines of code. It will be hundreds of lines, if not thousands.
Usually field operations are prepared instead of bit.
Where?
Instead of bit operations, it is preferred that.
Who prefers it? No, ultimately the computer will do only bit operations. So we are doing it only for to simplify the analysis, that's all. It is just a structured way to analyze. Ultimately what will happen on the computer is just bit operations.
Somewhere it is written that this algorithm's complexity is in bit operations.
Mm-hmm.
It's difficult to implement over field. Like Fidelia once.
I don't understand. Let's discuss after the class. Okay. Another thing in this algorithm is it is not just giving you a 1-bit answer, it is actually giving you more. So when it says that reducible, it has worked hard, it has computed the GCD, and there is actually some information you get. So for example, if big F was irreducible, in that case you will only get 1 bit of information. But if big F is reducible, then with factors having different degrees, right? So suppose big F has a factor, linear factor, and it has a quadratic irreducible factor. So those two factors actually in this GCD process will get separated. Do you see that? Because we are running I upwards from 1 to 2 to 3. So for I equal to 1, you would have filtered out the linear factors, all of them together. And for I equal to 2, you would have filtered out quadratic factors, all of them together. So yeah, that will need a slight modification actually. So when you compute the GCD with I equal to 1 and you get something, then you remove that from big F and continue the for loop. Okay, then you will get maybe quadratic factors, you remove them from big F and continue the for loop. So this way you would have actually gotten clusters of factors of big F. Okay, so a slight modification of step 1 you have to do, it is not exactly this, but
Otherwise it may repeat afterwards.
no, otherwise we are breaking, the program halts. As soon as it gets something, it halts. So you are not changing big F. So to achieve what I am claiming, you actually have to continue. Whatever you get, you remove it from big F and proceed. So you will get the linear factors and or whatever, the least I degree factors. So I1, then degree I2, then degree I3, and so on. Yeah, so let me just write down that observation. In the same time, similar algorithm, similar implementation. So we factor big F as product of GIs where each GI is obviously a polynomial over FQ. It is a product of equidegree irreducibles. So this is this code is also called equidegree factorization of big F. So so again, the big F will be actually factored into clusters. Each cluster will have equidegree irreducibles as their factors. Okay, this you do by whenever you find a non-trivial GCD, you remove that from big F by dividing. So that's a single division, and proceed with the quotient in the for loop. Is that clear? So this also takes same time. So this is in the same cubic time you can get equidegree factorization.
of one factor is more than one, maybe we need to repeat.
Keep updating big F as big F divided by the GCD that you have computed. So whatever GCD you will compute, you remove it from big F, and yeah, so there is this multiplicity issue. So because of that, you continue with the same I. In this case, you should go up to D. Okay, so at an I, when you get a GCD for the first time, you remove this part from big F, and then repeat the same thing for I. Maybe you will again get a cluster. This may happen because of repeated factors. So the same factor H may be repeating, which means H square may divide F. So the first instance of GCD will give you H, the second instance will again give you H. But after a while, degree I factors would be eliminated completely. Then you will go to the next degree, which is probably I plus 1. And you do this up to D minus 1. Okay? So if you carefully analyze it, it's the same time complexity, there is no change.
With the same complexity, we can also get the full factorization. The same, means if we get the cluster, we again do it, we get the same, we get the whole factor, the same complexity.
What do you mean whole factorization? You can find an irreducible factor.
Means all the, now you're finding clusters of.
Clusters, yeah, you can find the clusters, but those clusters are reducible.
But if it's apply the same algorithm on the clusters again, then we get the full factorization.
No, so
Same cluster again.
what do you mean by full? I don't.
Prime factorization.
You have to no, you cannot, this is not giving you irreducible factorization. We are not there yet. So that will take multiple classes. So in the first lecture, all you have achieved is what is called equi-degree irreducible factorization. So, or cluster factorization. So we have gotten clusters where the clusters may further factorize, but if they do, all the factors are of equal degree. But those equal degree factors, how to get to them, each of them, that we don't know. So at this point, this algorithm is oblivious to that, because x to the q minus x, for example, collects all possible roots. There is no way to distinguish between root 1 and root 2. So how will you distinguish them? That we will see gradually. So next time we'll achieve something, and after that we'll achieve the full factorization. Okay.